Okay. And so I'm very, very, I mean, sorry not to come because I really wanted to come, but actually I have to go. I'm in a foreign country, so I'm sorry not to be there because I really like to be there to speak with the students and people and also visit the lab. Unfortunately, it was I mean, it was not I mean, I have this problem. So my talk is dealing with knowledge extraction from medical imaging for patient-specific models. And here just to show you where is Compiègne, just in case where people doesn't know where it is. So it's a nice place. You see the big forest and so on. And of course, the castle and the UTC, which has been created in 1972. The objectives of my talk is to present you the methodology that we have developed in order to perform knowledge extraction from medical image and in order to develop patient-specific models for biomechanics system. So specifically how we can get the subject and patient-specific geometry, mechanical properties, and also boundary conditions from medical image. So this is just to show you some example that I'm going to illustrate you later. So why we are interested in patient-specific? Why? Because we do a lot of clinical research and also industrial research. And in that case, we need to have a personalized approach because I will show you later, because of the human variability, we have to we have to take this into consideration. Variability in geometry, mechanical properties, and of course, loads. And we all know that numerical models allowed us to have a better comprehension in order to improve the planification or the orthopedic or surgical treatment, but also it allows us to evaluate the external or internal devices, what we call orthoses or implants. So it means that the industrial application, it helps you to design orthoses, implants, diagnosis tools, planning preoperative tools, but always in a patient-specific way. So in order to do that, of course, I'm going to go fast on that because I know that everybody knows what are the finite element models. I mean, are used, of course, to describe and predict mechanical properties, behavior of bone, muscle, joints for a long time ago, more than some decades. And we all know that bone, muscles, and joints are complex structure in geometry, material properties. Geometry because it has complex curvature, shape, and material. We all know that there are different levels of organization. It also has a composite, what we call materials, interaction between mineral, organic components. And we do not forget that it is also a living biological tissue. So we all use physics, mechanics law, which needs basic assumption of continuum media. But I always recall, students or other researchers, biomechanics, biological tissue, are they continuum media? I won't let you the answer. I guess you know when you can use it or not, but this is a very big deal. It's really this big assumption that we all made. So just to recall, bone is a material alive. It is composite. As you can see some pictures, maybe you already know. Here you have cancerous bone, you have the compact bone. And if you look at the micro level, microstructural level, you can see that it is damaged, there is some holes. And here you can see the fibers very well oriented. So basically the material properties of bone, such as for example, cancerous or cortical bone, is somehow heterogeneous, anisotropic. You can see very well oriented trabecula, multi-hierarchical level, more or less organized. We could say the same thing for the cortical bone. Here you can see the multi-scale. See, this is a cortical bone. You know that it is quite compact, but if you look at 1 millimeter of the section, what you will see, it is a very quite well organized system that we call aversion system. You can see here there is holes. This is because it is the blood transportation. And you can see it is a sort of cylinder, and this is what we call osteon. And when you look at the osteon, you look at it in detail, you will have what we call the lamella that you can see on the osteon. And you also see the collagen fiber, which are connected here, more or less organized. And then if you go down another level, if I take this collagen fiber, it's made of collagen fibrils, you see. And then if I go deeper, a lower scale, you can see that the collagen fiber, it is a periodicity of interaction between collagen molecules and bone crystals. Really, when you work in this such system, it's very amazing because you can see it is very smart system somehow and well organized. So this is another picture where I can show you here again the osteon, just to show you the holes that you have. This is what we call the osteocyte canalicule. It is here. And you can see that this is the horse where the cells are belonging. It's just to show you that it is a living materials, okay? And here you see the cells, they have this kind of canalicule. It's because they can connect each other in order to have transmission, in order to have what we call the remodeling process, which is occurring all the time that you are listening to me. You have the bone remodeling process, which is occurring in your body. So this is really something very interesting, but that we have to take into account when you are working on biomechanical system. Again, it is alive. We all know that we have to get, old, this is reflecting the variation with age. Of course, you can see the spongious bone. So you have the trabecula, which are, becoming thinner. We have what we call the effect of bone mass loss. This is just natural. This is when you are born, then you are mature bone. Then when you are getting old, this is nature. You cannot go against nature, but this is life. So your bone is going to change morphologically, and you have what we call the bone loss. But this is a fact. But this is not a disease. This is just a fact that you have the bone which is varying from age, growth to senescence. So now I'm going to talk to you about the methodology. First of all, the geometrical properties. In order to assess this complexity, you have no choice. Now, everybody's using medical image. Why? Because this is the only way to get the geometry of the patient. And then most of the literature, you can see that most of people are using 3D slicer, materialized simpleware. We use our in-house software, and I will show you why we develop all our software, because we can control everything. So I'm going to show you this. Just some pictures, but not all. So this is, for example, the software we have developed for a long time ago, which allowed us to take a medical image and perform what we call geometrical, classical geometry that you can transfer to any kind of software in any kind of structural analysis software in order to perform finite element behind. Why I need to control the acquisition, I will say you later. Then the second step is to get the mechanical properties. This is the main problem when you are doing numerical simulation, is to get the data, okay? The data, what is the mechanical properties, what is the mechanical behavior, what is the load that you are going to take, and so on. That's a big deal. So in our team, I always perform in parallel what we call the determination of mechanical properties. And at the multiscale level, as you can see, organ, tissue, cell, molecular level, and also multiphysical, because each level is concerning a different physical properties. So you can have physical, chemical, and then you have to deal with the mechanobiological behavior. So this is what I show you for the bone, but you can say that you have the same thing for the tendon, and here you can have the same thing for the muscle. So again, I'm always amazed about the structure of the musculoskeletal system. You can see the bone, you can see the tendon, everything is connected, but we all look at one structure in another structure, but you have really to take this into consideration. Why? Because you will need somehow to build a constitutive law behavior. Somehow, if possible, reflecting the multi-scale and multi-physics behavior. I think that everybody has this aim, but it's very difficult because you have basically to have the knowledge to get the data, and you have to ask yourself also the reliability of the data that you have. So I'm showing you this, how we do this for the bone, which is for a long time ago now. So we do characterization on the same specimen, and we go through different scale. This is a challenging stuff, because using the same sample, then you have to respect, methodology, preservation, and all these things. So we use ultrasound technique, for example, and CT scan also for the image. And then we use cartography, we use transmission ultrasonic technique, which is somehow the only technique which allows you to get orthotropic material properties. And we also use nado-indentation for the microstructure, for the lamella of the osteon. And we can use also AFM in order to assess. Here you can see, this is a collagen fiber of human bone, which is very difficult to assess this kind of image, because usually you have this kind of image, you can see crystals, and then the fiber of collagen fiber. You remember the slide I showed you before. It seems very well organized, but when you looked, it's not so well organized, but there is a reason for that. Anyway, so that was for the bone. Oh, and this is just an example I want to show, because it was my first collaboration with LMS. It was a long time ago. It's in the beginning of the 2012, before 2012 and so on. And so basically, because of this multi-scale characterization, we were able to have the data of elastic properties of the lamella, the artificial system, and also the macroscopic level. And so we use, a technique which has been, a theory which has been developed at the LMS, which was based on variation approach on Ashin and Strickman, generalized for morphological patterns. So it allowed us, using this kind of model, to predict from micro measurements to predict the macro structure. It was very interesting, because I also have the macro structure, characterization. So it was very interesting to check the model and to see reliability of this model. But it is very interesting, this kind of model, because this is what I said to you, very interesting to connect the lower scale to the higher scale, micro, macro, and so on. You have the same thing for the muscle. So my colleague, Sabine Bensamoun, maybe some of you know her. So she's a specialist in characterization of the muscle, right? So you can see a muscle, this is on the right. So you can have the organ level. So you have to do some stress and some mechanical testing in order to have the mechanical behavior. And you have also to extract on this muscle the fiber in order to characterize also the multi-scale properties of the muscle. The most difficult part of the muscle is, your muscle has what we call an active part and a passive part. So in order to model this, sometimes you can use the passive way, but this is not his function. And usually we try to of course, to model the activation of the muscle. But in order to model that, you have to have data. Okay, so now how we can get from in vitro measurements to the in vivo measurements. That's the point. So why we want to do this? Because we wanted to do clinical application. And as I told you, we perform a lot of mechanical properties. And because of these results that we have found using mechanical properties characterization, we find that finally we have a variability, of mechanical properties. We can see there is heterogeneity. So all these kind of things that we have measured, and it is a fact that it is a variation, there is a variation according to the anatomical location. So all these things exist is a fact. So you have somehow to take this in consideration and how we can get this to the in vivo, how we can get this in vivo situation. This is just an example of the lumbar spine. So you can guess that the lumbar spine, the mechanical properties are different, makes sense, because L1 is a higher level, L5 is a lower level. So intuitively you say, okay, you have more load. So your bone has to react, has to adapt in morphology and also in mechanical properties in order to adapt to the load of the body, the head, and all the other things. This is just also an illustration of a femur. You can think that it is your femur because it's a normal femur. So you can see, again, an illustration of local heterogeneities. So you can see this is a CT, this is, density cartography. And here it is ultrasound cartography. So here you have the velocities, all right, from 3,400 to 4,600. So you can see that there is a variation. Of course, the thickness is constant, all right? So if you have the thickness which is constant, so you can imagine that it's illustrating the heterogeneity. Here, you can see that the values here are very lower for the velocities, and then it's changing. And here you can see the same thing, but this makes sense. It is explained by a higher porosity somehow, microporosity, because you have really to see it. I mean, really to play with the image to show you that there is porosity. If you remember the first time I showed you the slice of the CT scan, you won't see that. This is just because we refine the image so you can see really the local heterogeneities. And the main thing that you have to recall is that there is a variation according to anatomical location. And what is amazing, it's just to give you an idea that you can have until 40% of porosity. But again, this is normal. This is not pathological. So you can imagine that your femur, you have this kind of cartography of mature properties. So I said to you, we have mechanical properties in vitro. How we are going to get this in vivo? How we are going to get this? All right, first of all, remind that human variability, heterogeneity of mature properties, I said to you, have to be considered. That's why, since all this data, we always try to do subject-specific or patient-specific numerical models by considering, if possible, the geometry, we can get this, and mechanical properties derived from image. Of course, I'm going to show you how. I want also to record you, a lot of people are talking about subject-specific, patient-specific. I think that sometimes you have to clarify what is the specificity, because most of the people are using medical image. So if it's geometrical, everybody knows how to do that because this is the input data. But there is few work on specificity, on mechanical properties and also on boundary conditions. So our methodology or our secret somehow is that we are developing mechanical testing coupled with tissue characterization derived from medical image techniques. This is the way of doing. Since, I mean, we work on that field, I always try to couple mechanical testing with medical image in order to have correlation and data connected between in vitro and in vivo, because the image, you cannot get mechanical properties from an image. So you have to do mechanical testing. But then when you try to correlate, I mean, indicators from image with mechanical indicators, you know, biomarkers. So then you can have this link between mechanical properties in vivo and in vitro. So I will show you some examples for that. For the bone, it's easy. Usually we use CT scan. Now a lot of people are using it. We were kind of pioneer to do this because we developed a database for that. Thanks to the first database I show you for the Atlas. And of course, simultaneously, we perform CT scans. So it allows us to have really a characterization using medical image and mechanical properties. So this is, for example, the cartography of density, bone density. And here, this is a cartography of velocities. And you know the relationship, velocity is proportional to elasticity or Young's modulus divided by density. So it's easy for you then to apply the formula and get here what we have. It is the cartography of elasticity, the coefficient elasticity C33, all right? So it means that you can really be accurate according to what you want to do. This is for bone. For soft tissue, I'm going to show you example on muscles and intervertebral disc or IVD using MRI and MRE. which is a magnetic resonance elastography, and the other one is magnetic resonance imaging. So I'm going to show you some example on how we can get, mechanical data derived from this kind of image. So I just talked to you about the relationship between CT number and mechanical properties. So here you can see on the literature, so we provide some relationship. So a lot of people are using it, but I just want to recall that in order to use this, you have to have the measurements of the CT number. And sometimes people contact me because they say, the relationship, it doesn't work and so on. Why? Because they don't use the correct relationship. There is no continuum. So you have to use a relationship for cortical bone and also a relationship for conscious bone. There is no continuum. Even physically, there is probably a continuum, biological speaking, but mechanically speaking, this is really two different structures. Again, if you are using medical image, you have to use the same acquisition protocol than we have. If not, you may have a bias according to what you have, and then the use of the data. This is an example illustration. So from CT scan, you can get individualized geometric and material properties. This is just an example of two patients. You can see that young patient, it was a scoliosis study. You can see that the shape is different at the same level of the lumbar spine. And you can see that the distribution of material properties are different. This is just to point out that you have variability in geometry and elastic properties from patient to patient. Again, this is a fact. You have to know that it exists, but according to your project, maybe you don't need to take this into account, but sometimes according to your project, you have to take this into account because that makes a big difference. So this is just a fact and you have to play with that. According to, for the MRI, I just want to show you some examples, which is examples from a European project that we have been involved in. So for example, we use T2 mapping. T2 is time relaxation. You have T1 and T2. I'm not going into details, but the mapping of this T2 relaxation time of the spine, it gives you an idea of course, the hydrogen contents. So the T2, when it is low, it means that it is a little stiff. We use also another parameter that we call ADC, apparent diffusion coefficient. And this parameter gives you the motion of water. Again, recall that it is a spin, hydrogen spin. So if it reflects somehow the movement of the water and proteoglycans, which are very important, contents in the annulus fibrosus and the nucleus pulposus. So here you have the image of the T2 mapping. So here I told you that, okay, here it means that if it's low, T2, it means it's stiff. Here you can imagine this is the annulus fibrosus. Yes, it's quite stiff. Hopefully, makes sense. And here you can see that inside it is less stiff. And this is the first image that you can see in the literature that we show that there is two different things in the nucleus pulposus. Actually, if you look at the literature everywhere, you always see annulus fibrosus and nucleus. But here we can distinguish two different properties of the nucleus pulposus. So this was very interesting. And here, if you see the ADC, recall the ADC, it's an indicator of the motion of the water. So here, the more it is high, the more it is somehow liquid, less stiff somehow. So these parameters are very, very interesting and important for the disc characterization derived from medical image. So here we can distinguish different T2 for the three different structures. The nucleus here, it's one nucleus pulposus, but here we wanted to say B and C just to distinguish these values. Honestly, we don't know why there is these two structures yet, but this is what we observe. So what is interesting in the research that you observe things And sometimes you have to think why it is that way and try to explain and play with that in your project. Then once we have done that, so how we do, you remember I told you that this is the image, but then I have to do in vitro characterization, mechanically speaking, in order to connect my data from T2, from ADC, in order to extract, I mean, from medical image, biomechanical or biochemical data. So in order to do that, so we work again on the MySpine project. So we work with the team of gait-MRE and from Eindhoven University. So they provide us a 6 cadaveric specimen lumbar spine. So we perform the medical imaging analysis, and of course correlate this with the in vitro and in vivo in order to see if it is correct what we are doing. So this is just for the grade, the different grade of the disc. But finally, it's the protocol that we did was not so bad because we can see that there is some correlation about what we can find. And once we have done this imaging, we do the characterization very specific, very in a specific area. The PhD student, Mark, was coming there with us to compare in order to do the medical image assessment, characterization. Then when he brings back the structure, he knows exactly where he has to pick up the specimen in order to perform what we call biochemical properties of collagen, water content, collagen, glycosaminoglycan that we will call the GAG. So he will do this, and he also does other mechanical testing with the biomechanics lab of Ulm. Then it's very nice to do all this, but sometimes it's very disappointing because you have a lot of data and the correlations are not so good. You know, here you can see water content. This is a biochemical properties versus the relaxation time, T2, you know, for the different structure. And of course, sometimes some are better, but sometimes it's kind of frustrating to do all this work and to find some, this kind of data. But don't worry, we will exploit this data because they are very precious. So that was for the IVD. And again, for the bone, we have somehow improved our way of, modeling the mechanical properties into the finite element model of the bone. So it was a kind of a changing paradigm because we have developed what we call material-driven mesh generation derived from medical image. What is the deal? The deal is that I'm not going to mesh and then put my data, my mechanical properties in the mesh. No. I'm going to ask from medical image, I'm going to do the analysis. You know, this is a CT number. And then I can have all my relationship with Young's modulus and so on. And then I will choose what I want to model. If I want to model only cortical bone, I can give a range. I could have only finite element model of the cortical bone. If I want to do the finite element model of the spongious bone, again, I have to give a range. I can have a finite element model only of the spongious bone. Here, if I want to have the all variation, the all mechanical properties of the bone, I can do also. So here, the main difference between what we have done before is that the mesh is derived by the material properties that you want to model. So that was a big thing and very interesting way to handle things. For the soft tissue, so we are going to use the same software that we have developed. And then we are going to use it for the disc. And here you can see that in that way, as I told you, it is a material driven. So I can do the nucleus pulposus, I can do in red, I can do the annulus fibrosus. It's up to me what I want to model. So here you see you have the image, so I'm not going to do the detail, but here, see, we are able to do a mesh of the material properties that we have characterized. If you look at the literature, if you look at all the mechanical or finite element model of the disc, you will have only two structures, only the annulus fulosus and the nucleus, because this is what there is in the literature. This is what you see with the histological. You remember here, if I recall you, we see this. So this is what we see. So basically people are doing a finite element model of the annulus fulosus here and the nucleus pulposus. But here, the objective, not the objective, but the fact that we are using medical image, it means that there is a lot of rich information, which might be very interesting and of interest. You know, there is nothing gratis in our structure. So here you can see how we do. And here, see, I can, again, this is on finite element model. I can reflect the water content, respecting really the geometry and the biochemical properties of what we have observed on this medical image. Here we can show the water content, the gags, and so on. And then from here, again, okay, this is just biochemical data, but how we are going to use this data on the mechanical behavior law. So again, this is in a European project. So one of the team is expert in developing biomechanical behavior of the disc. And so they have developed what we call poroelastic materials. So we have published all of these things. I just want to show you how we connect things. So in this kind of law, you have this expression, and you can see that, again, also using literature, the coefficient K, which is there here, porosity, shear modulus, and so on. You can correct this coefficient with T1, T2, ADC, all the biochemical, all the MRI parameters I just showed you before. And all these things, P, for example, osmotic pressure, is also related to the concentration of proteoglycan. So we all have all this relationship. With our data, you can understand that we can connect this very easily. Easily, I say easily. You have PhD students working on coding, but then using this data to put on the finite element model. I won't talk to you about the finite element model also, because there is a lot of things to say on that project, but it's just give you the map, how we work. And if you're interested, we have also published all this data. What is very interesting also, this project we finished in 2014. It was finished, and the papers came out years after. So this is research, you know, it takes time to publish, but this is not always our fault for that. The time of publishing, I think, is kind of awful. So I have talked to you about how to assess mechanical properties derived from medical imaging. Now, what is very, very new is how could we access the boundary conditions or the muscle forces from what we call dynamic MRI or dynamic MRE. I will show you this later. So in order to do this, we developed, it's again on the MySpine project, we developed a protocol. Here you can see, this is what we call dynamic. You know, the difference between dynamic and kinetics and cinematic and so on. Here, you are doing this movement. We teach you how to do this movement. And while you are doing these movements, the image, the MRI is going to pick this image. So it's really you who is doing this movement. You understand why it is important for that. Why? Because here I can have your geometry in different position, but then I can model the muscle, which is, responsible of this movement. And in order to do that, we develop ourselves, again, a rigid body model using OpenSim. And then we put all the CT scan, all the, the extracted knowledge from the medical image in order to model this rigid body model. And this is a typical law which are inside this model. And here you can see, I can have the values of the forces. I would say estimated values. It's very important, estimated muscle forces for different position. Time, it's mean during the flexion or the extension. And this is some muscle. We have modeled 48 muscles, something like this. And this is just to show you closely the action, because when you are doing this, your muscles are activated. And our challenge is, our challenge is really to reflect this using this muscle, rigid body models. Here you can see this is CT scan that we have from the patient. And here we have the models of the muscle. And then using dynamic inverse, we can get this information. And from a muscle to a muscle, we can know exactly what is not exactly, the estimate, again, muscle forces values. These are somehow the first data of in vivo acquisition of the muscle, estimated values of the muscle. Sorry, I'm just, okay. And so it was a very nice example for you for the lumbar spine, because you can see that from a medical image, we can extract, I mean, of course, the geometry of the bone, the geometry of the structure, but here we can assess the mechanical properties from CT data. You remember for the IVD, we can assess the mechanical properties derived from MRI. And the load boundary conditions, this is what I just showed you via dynamic MRI. So this is a very nice example, the spine, to show you that we can from medical image, extract or get relevant information to perform patient-specific model. Another example is estimation of in vivo muscle during gait using elastography magnetic resonance. So you know that MRI and MRE, you know, basically the principle is to make the muscle, to perform a vibration, okay, of the muscle, and then you can measure the wave propagation, and then do some estimation of the muscle, passive and active muscle. Again, I didn't show you the picture, but here you can put the image, I mean, you can put the patient, but then the patient has to do some exercise, not exercise, he has to do some movements in order to assess the muscle passive and active. What I want to show you here already is why we say estimation of muscular efforts in vivo. Why? Because here, my colleagues, Tung, he tried to use different models, Voigt model, Springpot model. You can have a lot of models. Just with two models, I just want to show you that the estimation of forces is already different during the gait, okay, toe off and heel strike. That means that, you know, somehow the results, estimation forces is really, of course, depending on the model that you are using. Even though we can provide shear modulus, viscosity coefficient, we can provide this. Even we can provide data, there is a big, not a big problem, but there is still a bottleneck, is the choice of the mechanic of the law, I mean, the constitutive law that you want to choose. And this is just to show you that according to different law, you can find difference. So somehow we have to know that. We have to know that it is a fact. Another example I want to show you also for the how we can get properties from medical image. This is another project that we have since now 10 years. Is derived from the Equipex figure, which is led by Professor Bernard de Vauchel. I don't know if you guys know him. Normally, he's a famous guy because he's the first surgeon who has done surgery of the face, all right? I mean, a completely new face of a person who has been bitten by a dog, her dog. And it's very famous. And so we worked with him on that because he says to me, we don't understand how facial mimics is working. And so it's very difficult for people to do rehabilitation. You know, we ask you to smile, to do some movement, but you don't have any more or your, I mean, exact muscle and so on. You have somebody else, you call this a graft, you know. And so how we can deal with that? But then in that time, he says he realized that finally there is very, very lack knowledge of facial mimics, how it works biomechanically speaking, not with the face, because there is a lot of work done on the face acquisition and so on. But mechanically speaking, not so much. So what we did is we tried to, so we worked with a surgeon who has performed her PhD with us, and also other PhD were working with us. So here you can see we have medical image. So we have to develop the protocol. And then you have to be a very good specialist. That's why we work with MD. She's also an anatomist, she's a surgeon, but she knows exactly what the muscles are. And so then we develop a protocol where you can see the different facial mimics, such as smile, when you pronounce O, and when you pronounce poo. And then you can see just the zygomatic muscle, major muscle. So here, basically you have more than 20 muscles. But according to the surgeon, we are going to focus on these 3 muscles because they are the most effective, the most relevant in the mimic facial mimics, sorry. Just for you to have an idea, when you smile, your zygomatic in blue here, when you smile here, is changing his morphology. Makes sense because it's a muscle, so it's a soft tissue with high deformation, large deformation, and it is contracting. So when you smile, your zygomatic is contracting. And when you smile also, your levator angulis, so this is this one here, can you see the shape of what he's doing? It's amazing. It is completely twisting and changing. So when we have this data with my PhD student, Angxiao, at that time, we say, wow, that will be a very, very big challenge to model this, to describe mechanically this mechanical behavior. So this is research, you open the door, you don't know where you are going, but you know what you want to do, but the solutions are not so easy. So what we did, so we take measurements, from MRI, so asking the patient to do smile. So we have the natural position of the zygomatic muscle, for example, and for the smile, you can see the contraction. The same muscle, again, in a natural position, and then we ask him to do poo. We ask her to do O. You see, the different colors of the muscle is showing that the muscle, how it is deforming according to the facial mimics that you want to address. So I'm not going to show all the detail, but just to let you know that these experimental data are very, very important because it's allowed us to provide physical data for our mechanical behavior. Just for example, what we have using for the muscle, we did a lot of bibliography, we did a lot of trials. Finally, the models that we find the most, the most close to what we want to do, it is Martin's hyperelasticity for transversely isotropic biological tissue. But this is a model, but the contraction coefficient and so on is really deriving from what we have measured in using MRI. So now I'm going to show you the results directly. So here, this is the simulation using, the data of MRI. So I forgot to tell you that all the soft tissue, we also use hyperelastic, but I think it's a second order polynomial or something like this. So, but we have a lot of, things. So if you want to have some details, the papers has been published. She has finished her PhD in 16, but it takes time to publish. Here are some results. So if you want, I can show you later. Again, the simulation. So it is the same. So smiling, poo, and O. And tell you the truth, it takes time to get this kind of results. So we were so happy to have this because at the beginning, you can find very strange behavior of the muscle because it was not correct and so on. And here you can compare, you see the patient face, or here this is the patient, it is a subject face, and you can find again some, correlation of what we simulate and what we observe. And don't worry, we have data to compare physically. Now we can simulate with the other 2 muscles in addition of the zygomatus major. We can add this muscle, LLS and LAO, So this is just, for example, the position O. You can see that, of course, you have more accuracy of the deformation of the soft tissue and all the face. So we did this for O2, and how we try to evaluate the simulation. So she says validation, but I prefer evaluation of the model because the term validation, I don't use it anymore. But at the beginning, you always want to validate. For me, it's more evaluation of your model. So we use our data, MRI data from the skin, from the beginning, from the neutral position to the final position. Then you can measure the distance between the points, and then you can, compare this, what we call experimental data, with what you have done in simulation. And this is what she has done, and you see that relative difference is about 15%. I say makes sense because it's not so accurate, but it's not so bad, I would say, as a result. So this is just to show you an example of that. And then in order to not conclude, but somehow to conclude, the most important, what I have shown to you, is that it's very important to quantify the reliability of the numerical models. I don't use anymore the time validation because I don't think that it's depending. Sometimes you can really validate it. But when you start to do, data using in vivo and a lot of, information, I would say that I prefer to say reliability of numerical models in order to provide an objective tool for aided decision to clinicians. Because every time that you are developing numerical simulation, you have companies, you have surgeons, they say, okay, when I can use your model, at the beginning you say, oh, you cannot use it because I need to validate. Well, then they will wait forever because you can never validate a model for me. You can evaluate the reliability of the numerical models. That means that you can give a sort of probability of using this resource or not. But you have really to give your data to the surgeon or to the companies. Again, you have to know what is the reliability of your numerical models. Because if you wait, you will never get, a transfer of what you have done. And so for me, it's very important, this concept. And again, for the assessment of the knowledge geometry, mechanical properties, and so on, derived from medical image to the numerical simulation, prediction, it's important to have this reliability. First of all, what I mean by reliability. You have seen that everything I said to you is derived from medical image. It means my first input is the medical image. So I have to be worried, I have to be careful that my medical image, the input data, geometry, material properties, boundary conditions, and so on, experimental data have to be confronted with the predictive results. And the most important issue is the certification somehow of the data derived from medical image. It means that all the relationships that you have done have to be addressed, but somehow you have to be able to tell me, or I have to be able to tell you what is the accuracy or reliability of my data. I think this is very, very important. Why? Just a picture to show you. Here, this is the same section, same location. And you can see that if I take different acquisition parameters, I don't have the same thing as an input. First step, I work on this one or this one. Never mind, take one of these. Then I'm going to use same acquisition, but different threshold. So here you can see that according to the threshold that you are using, you can have completely different data. It means that you have hardware acquisition and software acquisition are also something that should be considered when you are using medical image. Second thing, I challenge you, I challenge everybody who's working in biomechanics field to say, I have chosen the best law to describe, this soft tissue and so on. I don't think it is possible. I think it's very difficult for me to say what law is the best. I have shown you some example. That means that you have always to try, that to test the sensitivity of the laws in order to be sure that, the reliability of your model. And for that, working for a long time on this field. So I say, okay, now a lot of people are using statistical models, which makes sense. It means that you are trying to test the reliability somehow of the data. Usually they use statistical models for mechanical properties and so on. For us, we prefer to use a certainty of the data. What we mean by a certainty? Because first of all, just some notion of uncertainty. You have what we call random uncertainty. Random is, I would say, somehow easy to quantify because you have to test the variability, repeatable acquisition, artifacts, hardware, software, human errors. All this, you can, it's random, but you can control somehow. This one, you cannot control. What we call epistemic uncertainty is just because there is a lack of information and knowledge. And so you are obliged to take this into account because you want to do a model, you want to do something, but you have a lack of information. So finally, what we did is also a new paradigm, is we try to get fusion from data, multiple sources, and then we don't use anymore, specific data. We use what we call an estimation. This is what I told you at the beginning. I like to use this term of estimation because I think that it is more correct. You know, it's like a sort of probability of the data, of the thymus, of the forces. You know, it's a probability data that you have to use. So basically, we have developed a work frame to model uncertainty, what we call pure box PD function theory. It's very well adapted for heterogeneous data, such as medical imaging, properties, physiological, and in each step, how it is propagated in the model. And what is very interesting is at the end, it provides you what we call the output confidence of your model. And then it's better to use that way because then you can, you know exactly somehow what you are doing. You don't say that I'm validating, this law is correct, this is correct. For us, now it's a long time I'm working in that field. That's why I have more of this approach. Well, finally, I didn't know, but it was the last slide of my presentation. And I take the opportunity to thank all the team of the MySpan project, which was very, very interesting. I always say to the students, if you can be in a European project, it's very useful. And this is for the FACE project with the MDs and the team I was working with. Voila, if you have some question, I will be glad to answer.